I hope my screen is visible.
Yes.
Okay.
You have to show full screen.
Yes. Is it show? Is it getting shown?
Yes, yes, now it is okay. Yes.
Okay. So a very good afternoon to one and all. Today I'm here to present my paper on random number generation for PKI using Controlled Anderson PUF. So myself Aditi Roy, I'm a research scholar in the Department of CAC of NIT Trichy. So my agenda will be introduction, problem statement, literature survey, proposed the PUF, Anderson PUF, then the implementation details, the results, and I'll be then concluding with some references. So talking about why we start with random number generation. So the fundamental aspect of information that is being communicated must be protected to maintain the message integrity, service availability, and the data confidentiality. So to cope up with the security needs of internet technology, various security layers are added on top of the TCP/IP transport layer protocols. So this security layers uses cryptography techniques. The cryptography can be of two types. One is private key cryptography, another is public key cryptography. The former uses only one key, and the latter uses two keys. So this public key infrastructure that uses two keys is a guideline which is having two keys for encryption and provides confidentiality and authentication. So here we can see in this diagram, the client is encrypting his or her message with a public key, and then the encrypted message is getting decrypted by this private key by the server. So here the public key needs to be stored in the client and the private key needs to be stored in the server. So instead of storing this cryptographic key inside these devices, we can have a special hardware structure called physical unclonable function. That is unclonable because it has no mathematical representation, transformation function or representation. It is hardware security primitive that uses the manufacturing variations to generate random sequences output. So this can be embedded in the hardware and can be used whenever it is needed on demand. It can generate the outputs. The other important aspect of public key infrastructure is random number generation, because any implementation of a secure cryptographic key protocol requires a secure random number which can be used as a key or nonce or both. So in an ideal world, all random number generators would be based on unexpected physical processes, for example thermal noise. But such systems are known through random number generators, but such systems are having some drawbacks such as high price, a large size, and so slow generation of numbers. These drawbacks make them often impractical for use. So our proposed approach will be overcoming these drawbacks, as we are talking about using PUF, Anderson PUF. So here all the existing TRNGs will be discussed on the PUF based TRNGs. So here in the first reference, STEM PUF has been used, where the randomness of the original STEM power and values is fairly low. First, let me talk about this STEM PUFs. STEM PUF works by using the flipping of startup values between different power on cycles. So next reference is also based on STEM PUF with combining hash function with periodic reseeding, but this has a drawback of large amount of memory. And the next reference is with based on RO-PUF. RO is string oscillator based PUF that works by creating a self-oscillating circuit using statistical variations of transistors and wires in the integrated circuit. So it has identical ring oscillators, that is called ROs. Um then the drawback is here worst entropy. Next reference is also this linear feedback shift register, where crossed SL latch and flip flops are being used with linear feedback shift register. But this technique is also vulnerable to key recovery attacks. Next, again, ring oscillators are used, but as we know that a ring oscillator need identical ring oscillators to be placed, and fixed placement and routings are needed. So this needs hard macros. This is a drawback here. So ROPUF with chaotic circuits are vulnerable to input-based attacks. That is shown in reference number 7. Then other references are again chaotic circuit with puff to generate the initial state. Chaotic circuits are this non-periodic oscillators that creates waveform that never repeats. So this with combination of puff, the use technique have this extra drawback of chaotic circuit implementation as it's analog based. So then logistic map algorithm, it is also a function that generates pseudo random number generators that uh, implementing a mapping function. The random numbers are generated. This also has the drawback of extra hardware. Then the double arrow of structure. Here also randomness is not good. And so the other tools are having a hard macros and two extra error correcting mechanisms. Then why we used this Anderson puff. First, this what is this Anderson puff needs to be discussed. So this first Anderson puff was proposed in reference number 13, which is shown here. There are two shift registers, and there is a carry chain which is having two multiplexers. From the shift registers, the initial values are given, which is opposite. If shift register B is having 1010 pattern, then shift register A will be having the opposite pattern. So this patterns will be acting as a select lines to both the multiplexes in the carry chain, and this output of the last ca- last multiplexer will be acting as a preset input, so that whenever there is a signal transitional hazards, that is uh, 0 1 or 1 0 glitches that we have in electronic circuits, where depending on that the preset input will vary and the output will vary accordingly. So this depending on this hazards, puff responses are generated. The puff's advantage where its use of within the FPGA computer aided design flow and its small silicon area. We are not using any extra circuit here. We are just utilizing the already available that logic cells in the FPGA circuit. So the next, there are modifications on Anderson puff, where in reference number 14, authors use NOT gates with flip-flops instead of shift register, so that puff can be placed into other slices. Slices are the logic the lookup tables in FPGAs are having configuration logic blocks that are consist of slices. So this Anderson puff does not depends on delay produced by the fast carry chain as well as the shift register. So in 15 reference number 15, authors suggested to employ the XOR gate, because there is XOR gate in the carry chain that can be used. So in reference number 15, they have used OR gates as well as the multiplexers. Then additional paths will generate sufficient delay because of the XOR gates. Then in the reference number 16, extra multiplexer were added to combine the challenge ability. But none of these papers investigated the randomness properties of the puff. So we modified this Anderson puff design, where you can see this we are having two shift registers and two carry chains. In one carry chain, four multiplexers, and with each multiplexer, one XOR gates will be there. So we are using this two carry chains, and there are two extra 2 by 1 multiplexer to add this challenge ability to the circuit. So the connection is in the design are as follows: the output from the shift register 2 is connected, the top shift register is connected to the select pin of the top multiplexer, that is called M5, and the output from shift register 1 will drive either the M1 or M2. So this driving of either there is a choice of selecting either M1 or M2 here in the multiplexer by using this extra two multiplexers, which is deriving by this shift register 1 output. So when the challenge input is 1, the shift register 1's output is directed to M2 select pin. Alternatively, if it is 0, then M1 is driven by the shift register, increasing the delay G. Again, in the top part, by using the XOR gate output and fixing the next select input of the bit delay width has been increased, the generated signal is carried till M5, the last level multiplexer, and then M5 is uh, generating the preset input to the D flip flop, and here from the D flip flop we are getting the response bit. So why such design we have chosen? Because there are four XOR gates with each block of carry chain. We wanted to utilize the FPGA fabric logic cells. So one of the there are four XOR gates with each carry chain block, and one of the XOR gate is used in the design. The additional path will generate, because such a way that additional path will generate sufficient delay. And the advantage of using this control signal is to have the choice of adding more delay or not. Here to add the multiplexer M1 or M2, whether we are driving the multiplexer M1 or M2, because here the output of the shift register 1, depending on the choice select line, challenge select line, it is driving either MU1 or MU0. So the output of MU1 or MU0 is driving M2 and M1. So like this, we are having the choice of adding more delay or not. So the shift register 1's output is directed to M2 select pin, and when CH is 0, M1 is driven by the shift register, increasing the delay G. The implementation details are as follows. The proposed PUF have been implemented on two kinds of devices. One is Zinc UltraScale plus MPSoC, which is uh, high-end board of 16 nm technology, and another is Zinc 7000 series associate chip Z board, which is 16 nm technology. Both of these are having different applications. Z board is having applications such as advanced driver assistance system, medical endoscope, professional cameras. And MPSC boards is having multiple cores, where it is having also real-time processing processors, and it has it has application of next generation advanced driver assistance system, and then 5G wireless, and then industrial IoT. So the complete PUF circuit was designed using Verilog HDL code, and no routing or placement constraint was needed in this design. So we have no constraint of fixed placement of routing. As mentioned, the proposed design make use of the configurable logic block resources that are available in
Aditi,
the FPGA fabrics by Xilinx.
Aditi,
Yes,
please conclude.
yes. Okay. So these are the results in IST test has been performed. This if p value is larger than 0.1, so sequences are distributed. So we are having random values. These are resource utilization. So as we can see here in the result discussion, in comparison with the other existing TRNGs, our proposed work has shown less area footprints than other existing PRNGs. So, concluding with this, I'll conclude like the motive of this work was to propose a good random number generator which does not take up more hardware resources. Towards this aim, the control Anderson PUF has been suggested, which can be utilized for cryptography applications. So it has been implemented using Xilinx Sync SoC device, and we ran NIST test correlation test on our PUF to ensure its randomness, and passed most of the tests. The comparison of utilization of resources has been shown. Okay, thank you. These are the references. Thank you. Any queries? Yes, I have done NIST randomness test.
Any questions or queries? If there are no questions, thank you, Aditi Roy.
Thank you, sir. Thank you.